Hi guys, this PowerPoint is going to be our lesson on volcanoes. I'm kind of disappointed that we have to do this in remote learning because I think volcanoes are pretty interesting and this is one of the cooler things we get to learn about this year, but we'll just do our best. I tried to make this kind of a visually interesting PowerPoint so that it's fun to look at as we go through. Make sure that you take really good notes on this as you go because volcanoes are the last thing in our unit for geology, so when we come back to school, we are going to have to take a test. And instead of doing a study guide, I'm going to let you guys just use your notes on the test. So the better notes you take now, the better resource you're going to have when we take the test in a couple of weeks. All right, let's get started. Okay, I think I've got my little laser pointer deal figured out here. So there are two main types of volcanic eruptions. There's explosive eruptions and there's effusive eruptions. So explosive eruptions are the type that, oh, let me click here. There we go. They're very powerful. There's a lot of ash associated with these types of eruptions. In fact, this one that's going on here has less ash than you'd normally think of with an explosive eruption, but they also throw big chunks of rock that are called volcanic bombs, and then smaller chunks of stuff. Any type of object that's created and thrown by a volcano is called pyroclastic material. So these explosive eruptions throw a lot of pyroclastic material like this away from the volcano during an eruption. So there's also the effusive eruptions. Those throw off little to no ash. It's mostly just kind of gently flowing lava like you see here. And the reason for that is there's a lot less dissolved gases trapped in this type of lava than this type, but we'll go into that a little bit more in a second here. Okay, so the way that a volcano erupts depends on several factors, the first of which is the composition of the magma that's fueling the volcano. So granitic magma, granitic sounds like granite, so this is magma that forms from melted continental crust, is much more explosive when compared to basaltic magma. Basaltic sounds like basalt, so this is melted oceanic crust. And a major reason for this is due to the viscosity of these different types of magma. So viscosity is a word that we use to describe a fluid's resistance to flowing, or like how thick the fluid is. So a fluid that is thicker and is harder to flow is described as being highly viscous or having high viscosity. So you can think of this as like water. When you're pouring water, water flows really easily. It has a low viscosity. It's not viscous, versus a fluid like honey. Honey is thick. It doesn't flow very fast. So honey is considered to be a fluid with high viscosity or highly viscous. And the viscosity of magma is really important because the more viscous a magma is, the more dissolved gases it can trap and hold onto and let those gases build up. And as the gas builds up, that causes a more explosive eruption versus when gas is able to escape slowly. So the more gas that's dissolved in the magma, the more explosive it is. This makes sense if you think of like taking a bottle of water and shaking it up and opening the cap. It's not going to explode because there's not very much gas dissolved within the magma. Compared to taking a bottle of soda and shaking it up and then opening the cap, it explodes all over the place because there's a lot of gas dissolved in that soda. So these three criteria are all kind of intertwined. Granitic magma, due to its mineral content, is highly viscous. It's really thick, and so that high viscosity allows granitic magma to trap a lot of dissolved gases and hold on to them so that they can build up pressure and produce more explosive eruptions. Okay, so we've learned before that magma is just molten rock from Earth's interior. There are a few ways that magma can form. First, you've obviously got to have heat. There has to be heat involved to melt the rock. Magma can also be formed by, we talked about this before, decompression melting, when we learned about the divergent plate boundaries and the two plates are pulling apart from each other, and that piece in the center has lower pressure. When you decrease the pressure on something, you lower its melting point. And then there's also water content, which we talked about. Water is volatile, so the more water there is within rock as it's descending into the mantle at a subduction zone, the lower the melting point of that rock is, and the easier it's going to be for it to melt and form some magma. Let's talk a little bit more about the two main types of magma. So first is the granitic magma like we have, let me get my laser pointer, on the left over here. So granitic magma, again, is granite based, made from melted granite, so melted continental crust. It's really rich in a mineral called silica, and silica, when it's in magma, makes it kind of thick and sticky. So these types of volcanoes are going to be the ones that form on land because it's melted continental crust. The eruptions are really explosive, and that's because of that silica making the magma so thick and sticky. It has a high viscosity. It's really hard for it to flow, so the eruptions are much more explosive compared to the other type of magma, which is the basaltic magma. So basaltic magma is basalt based, so melted seafloor again. It's very poor in silica, so that's why it's so much thinner and has such a lower viscosity compared to the granitic magma. These are going to be volcanoes that form in the ocean. The eruptions are effusive, so they're gentle. They're not throwing off a ton of pyroclastic material like a granitic volcano eruption would. The viscosity is really low, as you can see going on in the background on the right over here. This magma flows really, really smoothly and easily. And again, that's because of the absence of silica in this type of magma. So basic anatomy of a volcano is we have the volcano, which is like the mountain portion of this cute little guy in the background over here. The vent inside of the center of the volcano, there's a tube that's rising up from wherever the magma source is up to the surface. That's called the vent of the volcano. And then a volcano will have a crater at the top. They're not always as defined as the crater on this little volcano right here, but there is just some type of little collapsed crater at the top where the vent meets the surface. On to the different types of volcanoes. So the first category of volcanoes is called the shield volcano. And shield volcanoes are called shield volcanoes because they're broad and have just a slight dome to them. So they're called shield volcanoes because if you imagine taking like Captain America's shield and laying it down on the ground, it would form this shape with just this really gentle slope to it. Shield volcanoes have effusive eruptions, so they're more of that basaltic magma type. They're typically going to be islands out in the ocean. Some examples of shield volcanoes are all of the Hawaiian islands are shield volcanoes. Kilauea is the most active of the Hawaiian island volcanoes right now. And then also Iceland is an example of a shield volcano. It's a really, really big shield volcano, but it's the same kind of deal as Kilauea in Hawaii. On this slide, I just wanted to show you some examples of what shield volcanoes can look like when they're erupting. So you'll notice that the magma, well, it's called lava once it's outside, right? Magma's inside, lava's outside. I think you probably learned that in elementary school. So the lava at this point is able to bubble and flow around pretty fluidly, compared to an explosive type of volcanic eruption where it would be spewing ash all over the place. These just have lava that's just boiling away. This one in the bottom right over here, this is the volcano that has been actively erupting on Iceland for the last few years. The second type of volcano that we have is a cinder cone volcano. These are just little guys. They have a lot steeper of a slope to their sides than a shield volcano does. They have little eruptions, but they are more explosive in nature than a shield volcano, so there's going to be less liquidy lava involved with these and a lot more ash. Typically, a cinder cone volcano can only ever erupt once in its lifetime because they're just so small that they don't have enough magma to sustain multiple eruptions. So when it does erupt that one time, the magma will flow up through the vent and out through the crater and all that good stuff, but again, it doesn't have enough magma to support a very big eruption, so some of that magma gets stuck in the vent that's running through the center of that volcano, up from the magma source down here, up the vent to the crater. Magma gets stuck in the vent right here, and then over time cools and solidifies, and it pretty much just plugs the volcano so that it's never able to erupt again. On this slide, I just wanted to show you some examples of what cinder cone volcanoes can look like. So here's one that's getting ready to erupt. You can see a lot more ash compared to the shield volcanoes that we were looking at before. And it's just a little tiny mountain of a volcano here. And on this side on the right, we have just an old extinct cinder cone volcano. And you can kind of see in the middle here, if you look closely, you can see a little chunk of that magma pipe where the magma erupted, solidified, cooled, and plugged this volcano back when it was still active. Okay, and the last type of volcano, these are the biggest, baddest of the volcanoes. They are the stratovolcanoes. These are big honking volcanoes. They look like a whole entire tall mountain. They have huge, extremely violent, extremely explosive eruptions. These are the ones that form on continents typically. They're also called composite cone volcanoes because, let me get my laser pointer, because every time one of these erupts, it'll spew out a layer of lava that flows out, followed by a ton of ash. So if you were to cut through the center of this volcano and look at a cross section of it, it would be a bunch of different layers of ash and lava on top of each other. So that's why it's called a composite cone volcano. So the Cascade Mountain Range, which we talked about, is a continental volcanic arc, and those are all stratovolcanoes. Those are on the west coast of the United States. Mount St. Helens is the most famous one of those. It erupted back in the 80s. This guy in the background is actually Mount St. Helens before it erupted. And then another example of a famous stratovolcano is Mount Vesuvius, which is the one in Italy that erupted, and all of the ash that came out of it buried the city of Pompeii and killed everybody in it. So with this slide, I'm just showing you kind of what a stratovolcano eruption can look like. You've got a big mountain. This is Mount St. Helens before and after the eruption. So you can see a large chunk of the volcano exploded away during the eruption. And then in the bottom here, you can see just the vast amount of ash and pyroclastic material that explodes out of a stratovolcano when it erupts. On this slide, we just are going to start talking about volcanic hazards that can be associated with an eruption. So here we have an example of a lava flow. Pretty much lava flows are just going to burn anything that gets in their way. They're unstoppable. There's really no way that humans can fight against lava. So if you are a person or an animal or a car or a house or an asphalt road or a chain link fence, it doesn't matter what you are. If you're in the way of lava, you're gonna get burnt by it. So lava flows can either be really slow moving if the magma is thick and viscous, or they can be really fast moving. Unfortunately, you're going to have to go back and click on these videos on your own to watch them because the recording software that I'm using won't let me click on them from here, but they are valuable so that you can see just the difference between slow moving and fast moving lava. So the next type of hazard associated with volcanic eruptions is volcanic ash. Volcanic ash comes from more stratovolcano eruptions. So you can see there's a stratovolcano erupting in the background here. It's spewing huge amounts of ash out into the atmosphere that's then getting carried away by the jet stream. Volcanic ash is really dangerous because it creates such poor air quality. It's such a fine dust that it can get into like your car's engine. It can get into computer electronics and just ruin those types of machines. It's also really bad for people and animals to breathe in. If you breathe in enough at once, you can suffocate immediately. If you don't breathe in that much to die right away, it can still cause really severe lung damage because once the ash is in your lungs, it's pretty much there forever, and it can cause different types of cancers. And then we talked about this when we did our climate change unit. We discussed how volcanic eruptions can cause short-term climate change by causing cooling with all the tiny little particles of ash that get thrown up into the atmosphere are really reflective, and so as they get spewed out and spread around the globe, every one of those little particles acts like a tiny mirror and deflects a lot of the solar radiation coming towards the Earth. So you can get cooling of several degrees Celsius over a period of a couple of years, depending on the size of the volcanic eruption. And then over here in the corner is just a picture of kind of what the ash fallout looked like from Mount St. Helens when it erupted back in the 1980s. You can see there are several feet of volcanic ash here that have almost entirely buried this car. The next type of volcanic hazard we have is called the pyroclastic flow, which you can see going on in the background of this slide. So when you've got a stratovolcano that explodes part of the mountain away, a huge cloud of really, really fast moving dust and some lava and gases explodes out of the mountain. It's really, really, really hot. So if you get caught in one of these, you could just be burnt alive immediately if you're lucky. And if you're not lucky, and you're stuck in a pyroclastic flow, all of the ash and the gases that are associated with it will choke and suffocate you a little bit more slowly. So there again, there's a video that you'll have to click on your own that shows a pyroclastic flow that happened when a volcano it was either Indonesia or Japan, I can't remember, but there were some volcanologists that were going to study the eruption, and it erupted a little bit sooner than they thought it was going to, and so some of the people in the town and some of the scientists got caught in the eruption and were killed by the pyroclastic flow. So our next type of volcanic hazard is called a lahar. And a lahar is basically a flood of mud that's caused by a volcanic eruption. So this can happen either when the hot eruption melts any snow or ice that could be on the mountain when the eruption occurs, and then that water mixes with the dirt and ash and mud and flows down the side of the hill, or the ash that comes out of a volcano can also act as condensation nuclei for little cloud droplets to form on. So there's more clouds than normal, and those clouds get heavy and form a lot more precipitation than there would usually be. So that increased rainfall water mixes with all the ash and dirt and dust too and could create a lahar. And again, little video you gotta watch on your own because I can't click on it. Okay, moving on to formations that are created by volcanism. Extrusive formations form from erupted lava. So extrusive is like the lava has exited the volcano. These form above ground. So our first type of extrusive volcanic landform is a caldera, and a caldera is different from a crater because a crater always exists in a volcano. Calderas don't always. There has to be some kind of really large explosion out of the volcano that creates the caldera. This particular caldera in the picture is the caldera of Mount Hood, where Crater Lake exists. And Mount Hood is one of the giant stratovolcanoes of the Cascade Range. And then I just thought it was cool because Mount Hood in Crater Lake, this little volcano in the center of it is just a mini volcano that formed out of the center of the giant volcano. It's called Wizard Island. Our second type of extrusive volcanic landform is called a volcanic neck. And a volcanic neck forms when you've got the cinder cone volcanoes. Remember, those are the smallest volcanoes. They can only erupt the one time because they don't have enough magma fueling them. So this is the magma pipe in the vent of the volcano that all this magma couldn't get pushed out. You can imagine a long time ago the sides of the volcano used to be here, but whatever that rock was made out of was softer than this stuff. So the sides got eroded away over a long period of time, and you're left with just the chunk in the middle that never got exploded out of the neck. And this particular picture is of Ship Rock. This is in New Mexico on the Navajo Nation land. Okay, next extrusive volcanic landform is called a lava plateau, and a plateau is just a word for a wide flat area, and so a lava plateau is just a wide flat area of hardened lava. Remember when we talked about the moon, we talked about the basalt floods on the moon and how those were similar to the Columbia Plateau of the northwestern United States. So the Columbia Plateau is a bunch of basalt that got erupted out of really ancient volcanoes a very long time ago. So now we're going to move on to intrusive volcanic formations. These form from cooled magma. Intrusive is like inside, so this is magma that never actually erupted out of a volcano. It got trapped underground and then cooled, and then over a long period of time it gets exposed by weathering and erosion so we can see it above ground. Anything that's an intrusive volcanic formation is also called a pluton. The reason for this is because Pluto is the Roman god of the underworld, so it's like these formations formed underground in the underworld. First type of intrusive volcanic landform is called a sill, and a sill forms when magma injects itself between horizontal layers of sedimentary rock. So you can see in this picture in the background of this slide, there's sedimentary rock above and below, and then there's just this layer of basalt that's parallel to the rest of the layers. And the way that you can remember a sill if you're looking at a picture or a diagram is that the sills are sideways. They're like laying on their side like this. Okay, this is just an example of what a diagram of a sill would look like. If we were going to take a quiz or a test, I might include a diagram like this and say, what kind of intrusive volcanic feature is this? And you can tell that since it's sideways, it's parallel to the layers of rock above and below it. It's a sill. So you can see from down here, magma injected itself upwards and then just kind of oozed out onto either side, and that's what created the sill. So on this slide, I just have a couple more examples of what sills look like out in the wild. This picture and this picture, these are of a sill that's pretty famous in Glacier National Park. It used to be called the Purcell sill, but then they changed its name to just be the magmatic sill. So you can see this band here on this picture and this band here, this darker basaltic lava got injected into the rock of the mountains. So the mountains in Glacier are formed of limestone, which we learned when we did our earthquake safety, that limestone mountains formed as ancient seafloor a very long time ago and then got heaved upward by tectonic forces. So at some point, some basaltic magma injected itself into this limestone. And the interesting thing, especially if you look in this picture, you can see that there's like the grayish rock and then kind of a little whitish layer, and then the dark basalt, and then a whitish layer again, and then back to the grayish limestone. So when magma injects itself into limestone, it does a cool thing called contact metamorphism, and the heat of the magma cooks the limestone above and below, and when you heat up limestone with magma, you get marble that forms. So in this picture here, you can see there's limestone, little white layer of marble, dark layer of basalt, white layer of marble, and gray limestone again. Okay, our next type of intrusive volcanic feature is called a dike, and a dike forms similar to how a sill does, except for instead of being parallel with the layers of sediment, it's perpendicular. It cuts across the rock layers that it melted through. And the way that I like to remember how to tell what a dike is when I'm looking at a picture is because I think a dike looks like the spine of like a dinosaur or a dragon sticking up out of the ground. If you ever drive towards Great Falls, when you get to the other side of the canyon, you can see quite a few of this type of formation sticking up out of the mountains out there. On this slide, I just wanted to show you a few examples of what dikes look like out in the wild. So this one in the top left, this is a dike that is to the south of Helena. I'm trying to remember. I think it's on your way to Unionville if you were driving up to Park Lake. This is just a big granitic dike sticking up out of the ground here. Here's Mr. Benson. He's a retired earth science teacher from Helena High School. This is another example of a dike that's in Iceland. So you can see it's absolutely just cutting straight through these horizontal layers of sediment here, and that magma just injected itself and melted through those layers. And then down here is an example of just a really long dike that's partially exposed by erosion but not fully exposed yet. Okay, next intrusive volcanic landform is called a laccolith, and a laccolith is like a bubble of magma that never erupted as a volcano. It got trapped underground and then cooled. Another word that we use more commonly for laccoliths in Montana is a butte. So this butte in the background of this slide is called Crown Butte. And again, if you're driving towards Great Falls and you get all the way through the canyon and out onto the flats there's just this big honking butte sticking up out in the middle of the prairie. And this is Crown Butte over there. It was used as a buffalo jump by Native Americans thousands of years ago. Around Helena, a little closer to home, there's a very famous laccolith that doesn't have this really characteristic flat top shape of a butte. It's a little bit wonky shaped, and it is the Sleeping Giant. The Sleeping Giant is a giant granite laccolith. It could have erupted as a volcano at the same time as the Elkhorns were forming millions of years ago, but it never did. And so our little buddy to the north of town, the Sleeping Giant, is a laccolith. So next type of intrusive volcanic landform is called a batholith, and a batholith is a huge mass of magma that never erupted. So think of a laccolith, but like hundreds of times bigger even. On this slide, there's a picture of a piece of a batholith that's pretty famous. This is called Half Dome Peak, and it's in Yosemite National Park in California. So in Helena, we live on top of a giant batholith called the Boulder Batholith. If you look at, let me get my laser pointer, this map over here, this pink highlighted area is outlining the size of the Boulder Batholith. So it stretches all the way from Helena down south towards Butte. It's a giant granite batholith. And so because of the nature of this batholith being granitic, when granite decays, it forms a toxic gas called radon. And so a lot of people that live like in Montana City, Clancy area, they have to be careful to keep a check for radon in their basements because of all the granite that their houses are built on. That granite decays and it lets off radon gas. So the Boulder Batholith formed from the same volcanism that made the Elkhorn Mountains, which is if you just go outside and look to the south, like towards Montana City and Clancy, the mountains in that direction are the Elkhorns, and they're all volcanic mountains. And the Boulder Batholith, the volcanism associated with it is responsible for all of the rich minerals that are found in the Butte Hill, because the heat and pressure associated with volcanism can tend to concentrate minerals in areas. So that's just a little history of the Boulder Batholith where we live. So again, a cool diagram showing what all of these different formations look like. Something like this could definitely show up on a quiz or a test in the future. So over here on the left, you can see there's a dike. It's completely perpendicular to the horizontal layers. Sometimes a dike is just formed underneath an old volcano. So you can see this particular dike injected its way all the way up to the surface and formed a volcano. This type of volcano we would call a stratovolcano or composite cone. Remember earlier I was talking about how they have layer of ash and then lava and then ash and then lava after each eruption. So this could be an example of a stratovolcano diagram. This dike over here cut a little bit transverse across the layers, but it's still cutting across them, so it's considered a dike, and then it wasn't big enough to erupt outwards as a volcano. Here's a sill injected upwards parallel to the layers above and below it. Here is the little laccolith that never got big enough to erupt as a volcano, but it did push the layers above it up into a hill. And then over thousands or millions of years, all of these layers would get eroded away and the laccolith could be exposed. And then here is the giant batholith, which is pretty much the huge bubble of magma underground that supplies all of these other formations. Okay, so let's talk a little bit more specifically about how volcanoes can form. So this is a review. We talked about this when we did plate boundary stuff. Volcanoes can form at divergent plate boundaries. Typically the magma that fuels these volcanoes forms from decompression because again, well, let me get my laser pointer. I keep trying to point with my mouse. So again, as these two plates are moving away from each other, this center area here has less pressure on it because there's not plate forcing downward, creating pressure. So this chunk of the mantle can rise up and melt into a little magma chamber. So the examples we have of these are mid-ocean ridges like what we've got here, or also a rift valley like the Great Rift Valley of Africa is an example of a type of divergent boundary volcanism. So there's also convergent boundary volcanism. So when you've got two plates moving together and one plate subducts beneath the other one and then melts, and that melting rises up to form volcanoes. So examples of these are continental volcanic arcs, like in this diagram. This would be like the Cascade Mountains of the west coast of the United States, or the Andes Mountains of the west coast of South America, which would be like down here. So here's the Cascades, and here's the Andes. A volcanic island arc, so when you've got like two oceanic chunks of plate that are moving together, like here's the Aleutian Islands that we talked about, that chain of islands coming, that little tail that sticks down off of Alaska. That's an example of convergent boundary volcanism. And then I just wanted to make sure that I mentioned that all around the edge of the Pacific plate here, this is called the Ring of Fire, which I'm sure you've heard of before. But it's because this Pacific plate, in the center of the Pacific plate, there's a bunch of mid-ocean ridges, and so it's spreading apart and like moving in all directions, getting wider, and the chunks at the edges subduct below all the other plates, and you get a ton of this convergent boundary volcanism. So one type of volcanism that we haven't talked about when we did plate boundary stuff is called intraplate volcanism. So this occurs when you've got what's called a hot spot, so just a chunk of the mantle that's hotter than the rest. It rises up into the lithosphere and melts some of that lithosphere, and you can get volcanoes that form above that in the center of a plate, which is not typical. There's not a lot of these that exist on Earth. These are called hotspot volcanoes. The examples we have, like in this diagram here, it's Hawaii. So there's a hot spot in the center of the Pacific plate, and above that hot spot, you get a chain of shield volcanoes forming. So since the hot spot doesn't move, but the Pacific plate is moving over the top of the hot spot, all of the Hawaiian Islands are ancient volcanoes that used to be above the hot spot. So the big island right now is where Kilauea is, and that's actively erupting, but over millions of years, this plate's going to move this direction. So this active volcano here is going to move away from the hotspot and become dormant or extinct, and then a new shield volcano will form above the hotspot. Yellowstone. So if you think about Hawaii, it's in the center of an ocean plate, so they're basaltic shield volcanoes. But Yellowstone, down by Bozeman, is in the middle of the North American plate, which is continental plate. So it is a big granitic magma type of volcano, and the magma chamber, the mantle plume below Yellowstone, is so big that Yellowstone is considered to be a supervolcano, because whereas Hawaii is a pretty small island in the middle of a plate, Yellowstone is hundreds of miles across, just the caldera of that volcano. And then here's a video that you can click on that shows kind of the process of this plate moving over the hotspot to form Hawaii. Okay, we're getting close to the end here, so let's talk about some warning signs that a volcano is getting ready to erupt. Of course, this is important because people like to live near volcanoes because when volcanoes erupt and all the ash comes out, that ash is really rich in minerals and it creates really, really fertile soil. So people like to live near volcanoes to have that fertile soil to farm in. But they still need to be aware of the warning signs of when a volcano is going to erupt so they can get out of there in time. So first warning sign is a bulge on the side of the volcano. This happened with Mount St. Helens. You can see here before the eruption, it had smooth, steep sides, and then as it was getting to erupt, there was just this little poof that stuck out the side of it. And that's due to a bunch of trapped gases. So Mount St. Helens is a stratovolcano, so the magma is granitic, and granitic magma we talked about is sticky and can't flow, so it's really good at trapping gases. So the magma inside of Mount St. Helens trapped a ton of gases, and it just kind of bulged out on the side there. A couple more warning signs of volcanoes. You can get more earthquakes than normal happening in the area as the ground is shifting due to the force of the magma moving around and the trapped gases wiggling around underground. And then also the smell of sulfur can be common for some types of volcanoes. This is also called brimstone, like if you've ever talked or you've ever heard someone talk about fire and brimstone, like in reference to hell. Um, the kind of general conception of hell that is just like boiling lava and stuff. So fire and brimstone. And then if you don't know what sulfur smells like, you can think of when you boil an egg and then the yolk kind of has that weird stinky smell to it. That's what sulfur smells like. So if you can smell that around a volcano, it might be getting ready to erupt, because if the sulfur smell is out, that means it's starting to off gas, which means it's building up pressure. Okay, last couple of things here. The life cycle of volcanoes. So a volcano that erupts regularly is called an active volcano. Kilauea in Hawaii is an active volcano. This volcano in Iceland is an active volcano. It's just been burping out lava for quite a few years. A dormant volcano, on the other hand, is a volcano that hasn't erupted for a long time, but it still has an active magma chamber, so it could erupt at some point. Examples of these are Yellowstone, which hasn't erupted for about 640,000 years, so it might be due for one here pretty soon. And then Mount Fuji. Mount Fuji is, so Yellowstone's a supervolcano, and then Mount Fuji is just a regular old stratovolcano that is in Japan. So the last stage in the life cycle of a volcano is when a volcano goes extinct, meaning that it will never erupt again because whatever the source of magma was for that particular volcano is gone. So it can't erupt without a magma source. So the example of this would be Casey Peak in the Elkhorn Mountains, again to the south of Helena. Those are all mountains formed by volcanism, and so there are some extinct volcanoes there. All right, that was a lot. So let me know how this went. If this was a good way to do a presentation for notes, please let me know. If this was a really bad way to do a presentation for notes, let me know, because I have a feeling we're going to be having to figure out how to do this together for a while. Okay? All right. Thanks, guys.